working. So again, thank you, Mariam, for inviting us all, arranging this event and inviting us all to come. I think it looks very, very promising. So Mariam asked me to talk about IDA 30 years, to say something about this 30-year anniversary. And at first, I thought that, okay, the obvious thing to do is to talk about what things were like at that time when we started. For those of you who were not present at the time, to understand what it was like then, and for those few of you who were already there at the time, to relive the memories. But then, on second thought, I realized that probably I'm not the right person to talk about what things were really like at the time when IDA started. Because when we started, I came here with a vision for what research we should be doing and how we should organize the work. And having that vision, probably I did not observe reality very objectively, but rather I may have tended to interpret things the way I wanted them to be. So therefore, I think the best source of knowing what things were really like is by talking to the people who were here with me at the time. And what I can do is to talk about the vision, to talk about what were the initial ideas, and then I leave it to you to decide whether things came out the way they were intended, and also whether it really matters. So the time period I'm talking about mostly is the period from 1975 to 1983. 1983, of course, was the year when IDA was formed as a separate department within our university. 1975 was the year when I arrived to Linköping after having first started research activities in Uppsala, starting around 1969. And as many of you know, I did not come alone, but many of the members in the group that had started in Uppsala, at Uppsala University, came here with me. So we had a kind of flying start. So the department was formed in 1983, and then we've had 30 years of growth most of the time, and very fascinating development. The vision from the start was really in two parts. One was the research theme, and the other was how to organize the department. But both of these were very much influenced by what I had seen, partly at Uppsala University, which was and is a very traditional, old-style European university, and partly also at Stanford University. I spent 1 year at Stanford in 1966 to 67, and then I went back for visits a few times after. So with respect to research, the direction and the catchwords that we started with in Uppsala was, at the time, was small databases. So why small databases? Well, it was a kind of reaction against the title of a major conference at the time, which still is, the conference VLDB, Very Large Databases, which emphasized the problems of dealing with large quantities of data, large for that time at least. And I was saying, and we were saying, that actually there are many interesting issues which are lost if you emphasize the problems of size so much. And there are many issues which come up when you have very complex information, complex structures. Dealing with large size and complexity at the same time is not realistic. So why not deal with complex data? Today we might have called it knowledge structures or knowledge representation, but the term knowledge representation was not around at the time. So this was the emphasis, and this was at the difference with much of the thinking at the time about what computer science was like. Because then, I think maybe also today, but certainly then, there were two things which were considered very significant for computer science. One was abstraction. Abstraction in order to get away from the details of the trivial details and getting to the principles, and algorithms. Computers were seen as things that execute algorithms. So why did we go away from that? Well, let me take one concrete example. This is an example of the Cicerone system that Sture Hägglund did as his PhD thesis. So in Cicerone, the challenge was to build a system that maintains a small database of a street system, network of streets in a city, and that guides a user with telling where to get from point A to point B and giving advice about what he or she can see along the way. So this, of course, is something that is commonplace in computers today, in handheld devices, but at the time it was a topic for a research project and for a demonstration of concept. Because the idea was like this: if you look at the problem of Cicerone in a traditional, conventional way, then you would immediately do an abstraction. And you would say, look, in a city we have streets and we also have street intersections. So consider each street intersection as a node in a network, and then we have arcs in the network connecting street intersection to street intersection. And then once we've done this abstraction, we can go on to use graph theory and algorithms on graphs and doing the job. And our point of view and Sture's point of view was maybe that loses too much information. When you do abstraction, you throw away information, and that sometimes it's useful and sometimes it's not. And in the case of a street structure in a city, there is a lot of additional information and additional structure. You have main streets and thoroughfares, you have smaller streets, you have areas in the city which are fairly self-contained with respect to streets, such as Östermalm in Stockholm. So why is it really optimal to throw away that information merely in order to use a classical graph traversal algorithm? Maybe it's better to build a representation that catches all the additional information we have, because that will be useful for organizing research, hopefully, for providing auxiliary information, advice to the user, for attaching information about what are busy streets and what are calm streets, and so on. So it is in that sense that we said algorithms, of course, are important and useful, but they are not the major issue for us. Abstraction is important to an extent, but it should not be overrated. And this means also that languages for expressing algorithms, traditional programming languages, were not at the main center of interest. And languages for describing the structure, the meta description of data, conceptual schemata and the like, are not at the center of interest. We're interested in real information, the actual information that is in the application and that should be represented as well as possible. That was the idea. Of course, if it's only a theme like this, it doesn't help. It also needs a number of usages. So we thought there are a number of areas where this can be useful and important. In artificial intelligence, almost by definition. For natural language understanding, we thought also that it could be a good contribution to the area of conventional databases, so that they don't get stuck with too simplistic representation of information. And in general, we thought there are a number of applications where this kind of perspective on the information can be useful. But then there are other directions that could follow from such an initial theme. Programs themselves are usually seen as documents, pieces of text in programming languages. I think still, but certainly at that time. But we had the idea that why not treat a program as a structure? This was inspired a lot by the early contact with the programming language Lisp, and in particular with an implementation of Lisp called InterLisp, which took this idea of operating on the programs as structures to great length. For example, InterLisp was a pioneer in developing programming environments, support for software development that not merely does compilation and editing, but also does a lot of other support for users. That was started in InterLisp and then, of course, has migrated to conventional languages more during later years. Dealing with applications and classes of applications encouraged the use of special purpose languages as opposed to general purpose languages like ordinary programming languages. And if you're going to work actively with special purpose languages for a range of different purposes, then you need interpreters in order to implement them quickly. And if you have interpreters on a special purpose language, then the idea of partial evaluation in order to compile the special purpose language comes naturally. And so this was one of the things that was done in those early years. Partial evaluation was invented independently, I think chronologically first by Futamura in Japan, and then Dixon in the United States, and we were almost at the same time and did it independently. Yershoff in Novosibirsk a few years later. So what I'm saying is that just because we had this initial scene did not mean that we were oblivious to the issues of software and programs, just that we looked at them in a different way than what was conventional at the time. Okay, so this was the ideas for research, and as I said, these developed largely in the period in Uppsala from years before 1975, but they were brought when our group, or large part of our group, came to Linköping around 1975-76. Arriving here, there was already some activity. There was teaching of programming and of computer science under the leadership of Nils Lindekrantz, who was university lecturer at the time. Unfortunately, he passed away very soon after. A few people were also working with him, in particular Christian Chrysander, a few more who later on left the department. But Christian Chrysander is still here. So when it came to the question of how to build a department, how to organize an activity that could do not only research, as we had done in Uppsala, but also teaching, and be responsible for teaching and research and fitting them together. Again, I had two backgrounds. I had seen how it worked in Uppsala, I had seen how it worked at Stanford. And there were two important aspects where these were very different cultures. One question is, if you're starting to have quite a number of people involved and you need a structure for it, is that structure going to be hierarchical or flat? So what I mean is, by hierarchical structure, I mean the traditional European, or at least North European, structure of university departments, where you have a main professor at the top, and then you have assistant professors and associate professors and docents, and so it goes down the hierarchical ladder. And the flat structure is what you will see at, well, what I saw at Stanford, what you typically see at American universities, where if you go to the department webpage, you get a list of faculty, just a list of the names, alphabetically or whatever. And then for each of them there is a title. Some are full professors, some are associate professors, and so on. And each of them may have his or her own group of students. So the key difference between these two ideas is that in the if I may say so, the European system, the status of a person, the title that he or she puts on the business card, is strictly connected to the organizational structure. A certain point in the organization, a certain title. Whereas in the American system, organization is one thing and title is another. People can be promoted to the next level without essentially changing the organization. The other important issue is how much interaction and integration is there between the different units of work. Regardless of whether it's hierarchical or flat, you can imagine having groups that never talk to each other, each one doing its own thing. And you can imagine a situation where the people in the groups interact a lot. And again, I saw the difference between the two environments. One key aspect of the possibility of integration is what courses do the graduate students take as a part of their graduate education? Is it the case that each group, each laboratory in EDA terms, does its own graduate courses, and the students in a particular lab doesn't take any courses in any other group? Or is it the case that the department as a whole offers a graduate course curriculum and all the students obtain at least a reasonable breadth of courses from the entire curriculum? Again, different in different environments. For me, I thought it was very important to have a flat structure and to have an integrated environment for a number of reasons. Of course, these things connect together a bit, although it's not entirely coordinated. The flat structure, I think, is important because it provides a flexible promotion mechanism. It makes it possible to promote a person and emphasize appreciation of work without affecting organization necessarily. I think the breadth of graduate courses is important for the doctorand himself or herself, because it's what is going to be needed in the future career. If the person goes into industry, obviously, if the person stays in academia, you cannot expect to do exactly the same thing your whole life. So you need the breadth. For teaching, for doing good teaching, you need the breadth. And also from a structural point of view for the department. If you have integration in this sense, if graduate students understand each other's topics, then cooperation between groups is facilitated. And another aspect, which is, so to say, strictly organizational, is suppose you have a guy who is dissatisfied with his situation in one group. Well, if the set of courses is the same for the whole department, then it makes it much easier to move to another group. And maybe things are better there. So being able to move around is, so to say, socially important. So these were the priorities in starting the activity. And I tried applying this from the start. Probably the first instance of the principle was how we were able to recruit Bud Lawson, to our university. Because what happened when I applied for the professorship, then he also applied. He had the part-time position at the university, and he was also working at Saab, Data Saab at the time. So then we both applied, and there was a committee, and the committee proposed I should get the position, and there was a minority voice for him. And then according to the traditional script in the university at the time, at least, he challenged the decision. This was what usually happened. Somebody challenged, and then it went back to the committee, and then the challenger had to write the reasons why he should get it, and then the nominee should write the reasons why the challenger should not get it, or why he should get it. And typically this resulted in a certain amount of mudslinging that was difficult to forget afterwards. Now, Bud's challenge was written, not written in that way. It was very moderately written, and my answer was moderately written. And then what I did just after was I sent a letter to Bud and said, look, if this university is going to be serious about doing computer science, then they need us both. So please don't leave Linköping, try to stay around, and we'll try to arrange you get the professorship also, and then we can work together. And he caught on to that, and it didn't take long. He had also a professorship, and we were always able to work very well together. So I think this is one example of what happens. If you take seriously the principle that you need as much competence as possible, and don't follow traditional patterns for it. Bud's interest in computer architecture was important because he had been doing computer architecture, but he had gotten interested in VLSI design, which brought in concepts of hardware design languages and other things which obviously were related to computer science and to my interests, but not identical. So it was by no means identical to the theme that I described a few slides ago, but it was a very nice match. Then from that point things started to grow, and one important factor for the growth was the laboratory concept. Now in EDA, research groups are called laboratories, and this is sometimes generates questions from people from outside. A laboratory you would expect to be either a large room or a building or at least a large organization, but you use the term laboratory for research groups. Why do you do that? And the reason is historical. Because what happened around this time, 1977, 78 or so, there was a national organization called the Swedish Board of Technical Development, STU, that decided to start a program for building up computer science. The Natural Research Council was not really interested. What they did was each year in the application for increased government grants, they would write that datalogy is important and we want to emphasize it, and they got more money, and then when we sent in applications we didn't get any money from them. But STU took the point of view that they were in charge of doing things that industry needs, and at this point Swedish industry needs computer science to be built up, so they would sponsor computer science, even to the level of basic research. So I think that's an excellent attitude from that kind of organization. So then STU sent invitations for proposals to the different universities, and each of the major universities had the beginning of an activity, but by no means as big as we had in Linköping. We were significantly bigger in terms of the breadth of activity and size of activity. But of course there was a threat there, because they invited proposals for laboratories. And one could see that if there would be one laboratory in Gothenburg and one in Stockholm and one in Linköping, then the tendency would be for them to be of roughly the same size in terms of for the grants, regardless of whether we are more people. There is always a kind of inertia in an organization that does that. So therefore what we did was to send in a proposal for a software systems research center, which would consist of 2 laboratories. A programming environments laboratory and an application systems laboratory, and with a careful description of a topic for each of them, which was written so that you could see how they could mutually benefit each other, but they were really addressed different research topics. And this worked. This worked very nicely. And then later on we got more of these. Only a few years later we also got funding for an artificial intelligence laboratory in addition to these 2. Then in the years that followed, this laboratory concept evolved a bit. Partly because we were fortunate we were getting funding, so it worked in that sense. But also, I got hold of a very interesting book by a person called Richard Norman, from Finland but Swedish speaking. The book was called Service Management. So he was one of the pioneers in the area of characterizing service enterprises as opposed to enterprises that produce goods. And he had an analysis of what are the differences, what is it that characterizes service-producing enterprises that you have to keep track of, and where you should not just transfer the habits from goods-producing enterprises. That's a current issue today also, when we look at these various merit award systems for research and for teaching, which seem to be very much inspired by what goods-producing industry does. So anyway, some of his themes were that every employee is in the front line. You don't have any production plant where the employees are not visible to the customers. All the personnel are visible to the customers. This applies very nicely to university. We have people doing teaching, we have people doing research, and at least to the extent that the research is done in cooperation with industry, of course everyone is visible. So this means that personnel is the important resource, rather than buildings, installations, and so on. And then one of his key ideas was that in order for such a company to grow, the best strategy is to have a structure of modules which can be repeated sideways. So one of his examples is from McDonald's, where he said, look, all the McDonald's restaurants operate in the same way. So if you have a number of them and then you make one more, you can recruit one person for running it, and he or she can go to the existing McDonald's restaurants and get a lot of advice, and you can have the same organization structure for the new one as for the old ones. And these different restaurants don't compete with each other because they are at different places in the city, so they will, at least if you have a good attitude among the people you recruit, they will gladly share their experiences. This sounded like a good recipe for a university department also. Like we could have more and more labs, and we would try to set up a structure so that if we recruited new people of the kinds which were available at the time, the ones which were available for recruitment were people who came out just after their PhD. People with many years experience after PhD had already settled where they were, and they were not too many anyway. But people just after the PhD were potentially recruitable, and if we could say to them that if you come and join us, you get your own lab, You get only a moderate amount of teaching, you get a lot of independence, you get the full credit for what you do in leading your lab, and so on. That was attractive. So this is how the laboratory concept evolved, with a certain amount of ideology in it, but a lot of practical application, and it was successful in the sense that we got more and more laboratories. I think at the end there were 18 laboratories, and then the flat structure didn't work any longer. Then we needed to have divisions and laboratories within divisions. I should say a few words about the computer facilities also. That's a practical issue in a way, but it has been very important for the development of the department. If we had not had the right computer equipment at the right time, then we would not have arrived where we are today. So, of course, when I arrived here in 1975, there were basically no computing facility at all. There was a terminal to a computer in Lund University, where you would prepare your program as a deck of punch cards, put them into a card reader, it was sent to Lund, the program was executed, and you got a printout back. So this was ridiculous, especially having come from Stanford and having seen the time sharing in full operation there. And also because we had started to get some of that in Uppsala. So one of the priorities was to get a time-sharing system, and what was the ideal one at the time was the Dept system, which was more or less a de facto standard in research. Would we be able to get it? Was there a grant for it? Well, it turned out that at that time, the financing system in this university, like in the others in Sweden, was organized so that it made a distinction between subjects which were considered laborative and ones which were not laborative. So laborative subjects were like physics and so on, that needed laboratories, so they got more money per employee and per student. And non-laborative subjects were supposed to only work with pencil and paper. So the question was, what would autology be like, especially since we were in the math department initially. And fortunately, there was an administrative decision, not a decision by our faculty colleagues, but an administrative decision on the university level that autology was going to be laborative, which gave us a reasonable budget. And then secondly, there was an arrangement where you were able to, so to say, borrow money from the university against expected future income. So we could buy the system in 1977 and pay it over a number of years after. Very important for research. A few years later, the university purchased the second system as a resource for undergraduate teaching. And at the same time, they created a separate unit, the Linköping Data Central, for running the undergraduate teaching system. There was some discussion. We really had to fight some in order to get them to buy a Dept system, not because they didn't want, but because there was a central purchasing agency in Sweden, Statskontoret, that was in charge of making sure that the best computers were bought. And they tended to emphasize performance rather than fuzzy concepts like user-friendliness and so on. So, but we were able to convince them that we could buy the Dept for undergraduate teaching, although a conventional batch computer had somewhat better performance. And this only happened if the other departments promised not to complain. And they were very nice and didn't complain. But then after that, there was one thing that happened, which is actually the most acute conflict that I can remember during these years. And this was already during these pre-EDA years. We had purchased a Unix system for hands-on access. So it was a bit like having a personal computer today. We got one, and when we wanted to buy a second one, then this computer center complained and said they thought that they should do all operation of all Unix systems in the university because they saw that several departments were getting them. And from a total university point of view, there would be an economy of scale of them operating all the Unix systems. And of course, then the hands-on aspect that we had would be lost. And so I had to go to a number of meetings and fight this. Our argument was that with respect to competence, we need that competence anyway because we are teaching operating systems, for example. So we need the competence that is needed for operating the systems, and also our competence will be better if we have full access to the systems. And well, there were some stormy meetings, and finally we won that issue. That was also important, I think. It's one of the few conflicts. These years in this university have been much more peaceful than what people tell me is the case in other places. Okay, finally I get to how IDA started. So the situation in 1982 was that there was a mathematics department, MIE, which of course still exists, which consisted of two parts. One part in the Faculty of Technology consisted of mathematics, mathematical statistics, optimization theory, numerical analysis, and computer science, tautology. And within that department, in principle it was one department, but in practice it was hierarchical. These different groups were quite independent of each other. And maybe we were more independent than the others because we operated in different ways. And then in the Faculty of Arts and Sciences, still in the math department, there was mathematics and statistics and administrative data processing. So at that time, physics and chemistry was also taught in the Faculty of Arts and Sciences, and there was mathematics to go with them. And then in the electrical engineering department, there was a list of 6 or 7 fields, but in particular there was, well, computer technology, I think they called it, and led by Erik Sandewall, and there was a field that was initially called telesystem and then was changed to datorsystem, computer system, which was Bad Lawson's group and professorship. So then the idea came up that we had so many interests in common, in particular with Bad's group, we had such a size that we should be able to be a separate department. So should we maybe break out and make a new one? So the potential members in principle was tautology. This was the administrative data processing group, computer systems in the EE department, and computer technology in the EE department. And there were basically 2 reasons that were advanced in the discussions for making a separate department. One was bigger strength externally, being able to appear. For example, when we talk to industry or when we talk to sponsors such as STU, it would make much more impression if we could say we are a computer science department than if we would say we are in a mathematics department. And the other reason that we thought about was that this flat structure philosophy, as opposed to the hierarchical philosophy, was much easier, was held in common between Bud and me and between our groups, but not by the departments we were in, respectively. So this was discussed between us and with the faculties and with the university, and it was approved. And what actually happened was then that a new department called IDA was formed with several parts, which from the university point of view was 3 parts. There was tautology, there was administrative data processing, and there was computer systems. And Danielson's group decided not to join. And I think the major reason was not with respect to area of interest, but with respect to organizational philosophy. I mean, he was so strictly into the thinking about he running his own group and so on. Plus, he was very skeptical to some of the things we were doing. So then we had to have a name. And then, as you all know, the name that we ended up with was Institutionen för datavetenskap in Swedish and Department of Computer and Information Science. So why these? Well, of course, we couldn't call it tautology. It was natural to use the word computer science internationally, and then that translated to datavetenskap in Swedish. The administrative data processing group were a bit reticent about whether to join us or not, because they said in the mathematics department there was a separate part for arts and sciences, together with mathematics and statistics. And they worried if they would join us, they would be too small in comparison with the rest of the department. And they might not be well treated. And so I had fairly long discussions with Eva Svensson, who was the leader of the group at the time, to convince her that we would, in fact, very much appreciate their presence, and they would be valuable for us, and they would be well treated. And I'm fairly sure I can say that they did not regret that they made the decision to join. Now, what I just showed was the university perspective on it. For us, of course, with the idea about flat organization and so on, the department consisted of a few laboratories. So there was a programming environments laboratory, the application systems laboratory, artificial intelligence laboratory at the time. But Lawson's group at the time was called CAD Lab, for computer-aided design of electronics. And this is what has evolved over the years to the AS Lab of today, and then the ADB group. And as I said, this was a structure where new labs could be added easily, and they were. So this, I think, is as much as I will have a time to have a time for. We have 15 minutes, I believe, for questions and discussion. Is that correct? So, and I think it's important to have some question and discussion. But this is just a list of things that I would have talked about if there were a lot more time. The study lines, the D line we started in 1975, and the C line we started 5 or 6 years later. The teaching philosophy, which was under the leadership of Anders Haraldsson, who became the first university lecturer in the area after Nils Lindekrantz. The industrial cooperation, that was pioneered by Sture Hägglund, the SHARE program, kunskapsöverföringsprogram, knowledge transfer program, and other things. The initially defined areas and the initial vision that I presented to the work, and which I talked about first, of course, has continued both in the original labs and in a number of other labs, which have been created by splitting and also by the recruitment of other people from outside, such as Lars Arenberg, for example. There have also been new recruitments on all levels, also for areas that were not part of the original vision for tautology. For example, Jan Małżeński with logic programming as his main theme, especially when he arrived. There have been people inside who pioneered their own directions. For example, complexity theory, Christer Bäckström and Peter Jonsson. And then, of course, I have pursued my own research interests, and I've been happy to have a number of people who have agreed to work closely with me on that, such as Patrick Doherty. Many more names should be on the slide. I just couldn't name all. And if you look around in the room, you see that gives a concrete example of the impossibility of that. So if you're in the slide, that's great. If you're not in the slide, it's also great. At this point, I will stop and ask for questions and comments.